We're asked to use the fundamental theorem of calculus to find the area bounded by the x-axis, the line x equals 2, and the graph y equals x squared. So let's sketch that out here. We've got the graph y equals x squared. There we go. Maybe a little too asymptotic there. There we go. The line x equals 2. Let's put that here. Why not? That would mean the point here would be 4. And this would be the area we're talking about. X-axis, x equals 2, and the rest of the line. How would we write that particular area in integral form? Well, we would say it's the integral from 0 to 2 of x squared dx. How does that relate back to our fundamental theorem of calculus? This is our little f of x, little. And the fundamental theorem of calculus says if we can find an antiderivative of this little f of x, then we can plug 0 and 2 into that antiderivative and get the value. Well, fortunately, we've been given a little bit of a guide here. The derivative of 1/3 x cubed would be, okay, now we're just doing derivatives. Bring the 3 down front. I get 3 over 3 x squared, and of course that's equal to just x squared. So we can use capital F of x, or big F of x, as 1/3 x cubed. And so by the fundamental theorem of calculus, our integral is equal to 1/3 x cubed. And I'm going to introduce some new notation here, between x equals 0 and x equals 2. This notation here, sometimes it's called big bar notation, indicates that we're going to sub in x equals 2 and then x equals 0, or evaluate the function at x equals 2, x equals 0, and subtract. So that would be our 1/3 of 2 cubed minus 1/3 of 0 cubed. That is literally our f of b minus f of a in the fundamental theorem. We found an antiderivative. Now we're subbing in the values 0 and 2. And at the end of the day, we're going to get simply 8/3. So this area is exactly 8/3. Now, it's worth noting this is a major accomplishment, what we just did right there. Up until now, if we'd asked you what areas you could evaluate, it would be triangles, rectangles, and circles, or things built out of those. This is the first time we've been able to compute exactly the area under some arbitrary curve. And we can use this technique much more generally than the simple triangles and circles stuff that you've seen before. So this is a real gateway into finding or evaluating areas that would have been completely impossible without the tools of integration. Okay. It's worth exploring a few of the options and alternatives here. We used the antiderivative 1/3 x cubed because when we differentiated that, we got x squared, and that was good. The question is, could we have picked anything else? Is there another function that we could pick that, when we differentiate it, gives us x squared? Well, I think we all agree that if we're going to differentiate something and get x squared back, it better have an x cubed in it. That's the only way to get an x squared when we differentiate. And if I'm going to have a 1 here, the only way to make that work out is to have the third, so that when we differentiate, the 3 comes down front, and we get 3 and 3 canceling, we get 1x squared. What we could do, though, is throw something extra on the end. We need this, but maybe we could throw, a 5 on the end. And if we do that, we still get x squared when we're done. So adding a constant on the end here doesn't change whether this magical antiderivative still gives us x squared when we differentiate. However, it turns out it really doesn't matter if we add that plus 5 on the end. Let's see why. Because if we do our fundamental theorem, we're going to take the integral of x squared. We know that's going to be 1/3. Let's use this formula this time. 1/3 x cubed plus 5 evaluated at x equals 2 and 0. And that will be 1/3 2 cubed plus 5 minus 1/3 0 cubed plus 5. And what we notice, thankfully, is that this 5 here is going to get canceled perfectly with the negative sign, because we're doing the difference of f of b minus f of a. Whatever constant we choose to put on the end here will always cancel out, and we will get exactly what we had in the simpler version, which is just 8/3. So there are other antiderivatives, but they don't have an impact. Choosing one of them instead has no impact on the final area calculation with the fundamental theorem. Plus c, or plus 5, always cancelled with minus 5 from that f of b minus f of a. All right. Well, if that's the case, then we can generalize even further. We know that our function could be 1/3 x cubed, or it could have been that plus 5 or plus something else. And here's where we get the famous plus c, where c is some constant, some unknown constant. When we antidifferentiate x squared, we're going to have 1/3 x cubed plus some constant, and we can check that that's actually the case. That doesn't matter what that c is by differentiating. By taking the derivative of 1/3 x cubed plus c, of course, gives us 1/3 3x squared plus the derivative of a constant by itself is 0, x squared, and all of that is regardless of the c value. Doesn't matter if I put plus 5 or minus 20, the derivative will still be the same, because the derivative of that constant will always be 0.